right. And I'm going to share a screen as well as we get started. Okay. Welcome, everyone. I am Mary Dussault, and I am a educator and science education program manager at the Center for Astrophysics, Harvard and Smithsonian. And I'm also part of the NASA's Universe of Learning Consortium. And this is the second in a 3-webinar series about exploring exoplanets with NASA's Universe of Learning. Back in November, we kind of had an introduction to some resources from Universe of Learning, and today we're gonna, today's subject is how to participate in exoplanet science. So if folks want to introduce themselves in the chat and where you're from, that'd be great. I am going to, the agenda for today is a little bit of an introduction to NASA's Universe of Learning, and but the main part of the agenda is to give you a tour through our DIY planet search portal to the MicroObservatory robotic telescope network, which allows you to kind of go through the whole process of collecting data of real exoplanets, analyzing it, and seeing if you see the telltale signal of an alien world around a star outside our solar system. So we'll also get a little bit of input from some educators we have on the line. A lot of the folks on this webinar I know are educators, and hopefully we'll get a little insight on how it's gone with their classrooms, and then we'll look forward. So on the webinar today, the members of NASA's Universe of Learning who are here, and actually I don't know if Rachel has arrived, Erica, maybe you know, but anyway, myself, Erica Wright, and Frank Sigowitz are all part of the MicroObservatory team here at the Center for Astrophysics. Rachel is part of the Exoplanet Watch team at JPL, and we'll actually be going into more detail about that project next time when we have our third webinar in January. So a little bit of just overview. What is NASA's Universe of Learning? It's a it's funded by the NASA Science Mission Directorate, and it's specifically a STEM engagement program from NASA's astrophysics research missions. And so the idea is to engage learners from all backgrounds in experiences that help them explore the universe for themselves. And so we think today's topic is an excellent example of what NASA's Universe of Learning tries to do. In particular, astrophysics at NASA covers these big questions. How's the universe work? How do we get here, and are we alone? And of course, exoplanets are part of asking that existential question, are we alone in the universe? And so that's kind of how we fit into the NASA's Universe of Learning portfolio. Last time in November, we learned about some learning resources, hands-on learning resources, online learning resources, visualization learning resources, and we heard from an exoplaneteer, a professional researcher, a grad student, Juliana Garcia Mejia, who did a great program, gave us some background on exoplanet science, and the link to that recording is in the MicroObservatory YouTube playlist for this series. I dropped it in the chat earlier, but we will send that link to all the registrants for the program, so you will get that link. So this time, the subject is how to participate using the DIY Planet Search interface. And maybe I could just get a show of hands. If you can raise your hand if you have used DIY Planet Search And I'm seeing some physical hands raised on the screen. How about those hands in the participant list? When I think there's a little raised hand. There we go. Lots of hands. Okay, but lots of unraised hands. So we've been making some changes to the DIY interface that I think some of you will be interested in, and we are going to continue to make those changes. So we'll want some feedback from you as well. So the DIY Planet Search interface, you can get to it at microobservatory.org, or we have a bit.ly here, bit.ly/DIY Planet Search, and the capitals count. So you have to have capital DIY and capital Planet, initial cap Planet Search. And that'll get you to this site, which you want to create an account so that you can collect your data and keep it. And that's what we're going to talk about, what you get to do with real data and how the site is set up. Erica, I hope that you will interrupt me if somebody asks a question that's timely, okay? And the DIY Planet Search basically uses the transit method. We learned about that the last time. Essentially, one way and a key way to discover exoplanets is to look for a dip in the light of a star where the plane of the planetary system happens to be lined up with Earth, so that there's an eclipse as the planet goes around that star. And there's a lot you can learn from the transit method because the size of the planet affects the size of the dip in the light. The distance of the planet affects the timing of the transit, and there are other things to learn as well. So obviously we don't see stars like this when we look through a telescope. Oops, sorry, all right, can I? We use telescopes like these. It turns out you don't need a space telescope to detect an exoplanet. You can use a pretty small telescope, and our MicroObservatory robotic network is made of 6-inch aperture telescopes, which happen to be a great size for detecting some of the largest exoplanets, what are known as hot Jupiters, because they're big like Jupiter and close to their stars. So they go around their stars really frequently, much more frequently, in fact, than Mercury goes around our star, because they're typically far inside the orbit of Mercury. But 6-inch telescope is enough to detect that signal, and we'll see what that looks like in a little bit. We have a telescope in Tucson, Arizona, at the Whipple Observatory that is dedicated to observing exoplanets. I have to stop touching my mouse. Excuse me for going back and forth in these slides. And the telescope in Arizona, one of these two telescopes in Arizona, is dedicated to observing exoplanets almost every night. 4 nights a week. Typically, we are gathering data on exoplanets, and that data is yours for your own analysis, and you can request that data to your very own DIY Planet Search account. For those of you who are educators, the neat thing about DIY Planet Search is it really enables students to experience pretty much all of the science and engineering practices, from asking questions to thinking about how to carry out this investigation. How are they going to split up the data collection and analysis among a group of students, analyzing and interpreting the data, mathematical thinking. All of this is involved with real data. and some of the ambiguities of real data are involved as well. And that's something you often don't get in canned labs or things that you might do like that. So here's what DIY Planet Search enables you to do. Essentially, you're going to use the telescope to take a bunch of images of an alien solar system. You're going to measure the star's brightness and then analyze the results, graph those measurements, and then analyze the results. Now, I'm going to stop here and ask you to either type in the chat or you can unmute yourself. We're here if you want. What are some questions about how to set this up? What are some questions that come up about how this is done if you're going to actually detect an exoplanet? What do you need to know? Because you're about to control a real telescope and ask it to get data. What do you need to know to carry this out? Where to look? When to look? Okay, yeah. Where to point the telescope? Which? When? Which star? Yes, yes. All the right. You need some information. How is scheduling managed? Assuming you have more users than scopes. We'll get to that in a minute. Yeah. So the first thing you're wondering is how to set up the observations. So I'm going to go to the tools section of the DIY Planet Search interface here. And I'm going to kind of go through slides, but at some point I can go live to the actual interface. But I'm at this point going to keep myself not going off on a tangent by using my slides. Okay, so once you click on the DIY tools section of the DIY Planet Search, we kind of really scaffold the process of collecting data through these steps that are on the left side of the menu, scheduling your target. And so we do that for you. Frank, who's actually on the line each month, looks ahead a month and he determines an observation schedule that the telescopes are going to pursue. You get to decide which of these data sets you want to collect into your account and analyze. And somebody asked about a little earlier, how is scheduling managed if you have more users than telescopes? Let's see, tonight, if you wanted to look at the star that's scheduled tonight, and 1,000 other people did, you can all get that data. The same data would be put in all your accounts. So that's kind of how we deal with more users than telescopes. So this is really a universal interface to use real data and to see if you can detect a transit. So we have tools for scheduling. As you can see, there's a lot of, these are all names of planetary systems. Last month, we learned about how you could explore planetary systems using eyes on exoplanets. So any one of these, you could go back to eyes and kind of get a visualization of that planetary system. But by clicking on the data set you want to see, you then go on to determine the images you want to collect in the period of time. When you first look at this page, you could see that this Corot 2 observation, which was back in June, the observation was scheduled over 4 hours from midnight through 4 a.m. And every 3 minutes. So MicroObservatory basically takes an image every 3 minutes. And depending on which ones you request, those are the ones that wind up in your account. If you're an educator, and our educators can possibly talk about this or pipe up, you can split those hours among your students. So different students are analyzing different parts of the data set. You select an exposure time and filter. At this point, all of our targets pretty much are 60-second exposures. We are investigating some brighter targets that may have a shorter exposure time, and at that point, the scaffolding will help you understand whether you have a brighter target or a dimmer target. So after you schedule your target, after you schedule your target, the next day, if you've asked for a target that night, or immediately, if you've asked for a target that was a prior night over the past month, the data will wind up in your account, and you can use the DIY Planet Search measuring tool to measure the brightness of the stars in your image. And so the innovation of DIY Planet Search is that there is a photometry tool, a tool for quantitatively making measurements of these images right in the browser. You don't need to download software, and the data is collected in your account, and if you're with a group of students, in all your students' accounts right in the browser. So this is what the data looks like when it comes back, and you notice that the interface has these 3 little measuring circles, and those you basically just use your mouse and you place them over the target star and 3 comparison stars, 2 comparison stars, to make your measurements. Now, the thing to really understand about astronomical images that come from CCD telescopes is that what comes back from the telescope isn't really an image. It's a bunch of numbers. And every pixel on the detector basically had photons of light coming from the field of view, and the more photons of light that fell on that pixel, the higher the pixel value. And so it's the pixel values behind the image that you're actually measuring to determine whether the star is dimming over the period of the observations. I noticed there's a couple questions here I want to see if I can answer here. Let's see. Jeremy asks if a planet, when should you start your observation? How much time to observe? What if the star is much bigger than the planet? It would take a while beyond classroom time. I'm not sure I'm understanding Jeremy's question. The telescopes, again, the MicroObservatory interface, the MicroObservatory scheduled observations generally cover about an hour before to an hour after the predicted transit time of any of these targets. So we are observing targets that are predicted to have a transit. They're already discovered. Now, the predicted time doesn't always exactly match. And in fact, this is where your observations are the real results, right? So I think I might have answered the question there. we'll come back to that later.
So actually, Emma's clarified, and I think that might be, Emma here thinks he might be asking.
Yeah, okay. So I will show you how you do not have to actively monitor. You make the request, and if the observation is in the future, the night that request is made, the next day, those images will be collected into your account. You don't have to do anything about it. They'll appear there. If it's a data set from the past, the data, you can ask for it and it'll be immediately scraped up into your account for analysis. So you don't have to monitor these telescopes. The telescopes go off and do the work for you to collect the data, and then our system puts them in your account for measurement. Okay. Yeah. Okay. So here's the measuring brightness page on the DIY Planet Search has a bunch of video tutorials. These are very useful in terms of figuring out, understanding your image, understanding how to find your target star, because you've got this field of dots. Which one is the star that's purported to have a planet passing in front of it? And then there's another tutorial on the actual brightness measurement. And so I'm going to just play this video of that process right now. So there's a finder for every target star that's like a little transparent map, and you can place it until it matches your actual data underneath. And we've marked the map with a T and two C's that are the target star and two comparison stars, because the only way you know if your target star really dimmed, as opposed to a cloud just went by it, is to calculate its relative brightness compared to stars that don't have planets passing in front of them. And so you can see on the right the pixel counts of the measuring circles of the target star and two comparison stars. And when you hit calculate and record, the DIY interface calculates the relative brightness of the target star compared to those two comparison stars. And so at 1 a.m. in that data set, the relative brightness was 0.79 or whatever that was. And each time you open a different image, you can make a new measurement, and over a class of 20 students or a group of 20 students in a workshop, if they each make 5 measurements in 100 image data set, it won't take too long before they generate their what's called a light curve. And actually, whoops, let me stop there. There we go. So here, in fact, are some data points that were collected by a student in a group, and doesn't look like much, right? There's a bunch of dots. Again, in that measuring brightness tool, you see these 3 tabs. The Analyze Image tab is the window in which you select from your data, and I'll show you how to do that live in a bit. But the Graph Brightness tab gives you your measurement after you click and record. Here's the whole group. So this is one student, and here's the whole group. So now you can see something that really does look like the star had a definitive dip at a certain point in time. And it looks a little messy. It doesn't look like the theory in the books. And in fact, the data can get even messier than this. So the question is, there are lots of things you can do to have students think about how strong can they, how strong is their conclusion of whether they've seen a transit in the data. We have a interpret and share tool. So once students have, I was hoping I could actually use an, oh, I do have an annotate. Here we are. Let me do that. There we are. Okay. So this, if I were to draw what I think the average of all these dots were across time, I might do something like that. Right? And the interpret and share tool allows you to set where you think the baseline of the data before and after the dip. And this green line is the where you think the average of the dip is, because again, these points are all kind of scattered around a model transit. So here I'm fitting the data with my hand drawing, and you can use these lines in the tool to fit the data as well. And the depth of that dip is actually related to the size of the planet. It's related, actually, I have to erase everything here. There we go. All right. It's related quantitatively. You can figure out the square root of the percent dip actually tells you the size of the planet in relation to the star it was passing in front of. So if you get a dip of 4%, if you get a dip of 4%, then the planet is about 1/5 the radius of the star. If you get a dip of 1%, the planet is about 1/10 the radius of the star. And of course, 1% is a pretty tiny dip. Pretty tiny dip. And as Frank points out, the host stars we're observing are dimmer than naked eye. They're around magnitude 10, what astronomers call magnitude 10. And they're typically, the planets are typically a size between 1.5% dip to a 3% dip. And you can detect that in the data. So we have observers using DIY Planet Search all over the globe. And I think some of the people on this call are also some of our observers all over the globe. And anyone can use the DIY Planet Search interface and can publish their results for others to see. And when you look on the community page, the community results page in DIY Planet Search, you also have an opportunity to compare your own data set with data sets of others and with data sets of the same target, but taken at different times. Now, I want to make sure we have a chance here to hear from our educators about how this is used with a group, but I also wanted to go to the live site. If actually, why don't I ask for questions at this point, and then Jim and Enrique, you can go first if you want and tell us a little bit about how you've used it. And if you need any demonstration of the live site, I can do that, but you could also share a screen. So any questions people have at this point about how the interface works? I'm actually gonna go to the interface here. Enrique, why don't you tell us a little bit about how you've used it? If you want to share a screen, you'd be welcome to.
Mary, can you hear me?
Can you get a little closer to your mic?
All right, I'm hoping I can. Can you hear me okay?
Better,
Maybe I'll just use my teacher voice. How about that?
better.
Yeah, I'll share my screen if you're ready.
Very good.
Okay.
Hang on, and I will, Erica, can you make that possible? Wait, I think I can. There we go. All right, you should be able
All right,
to.
let's see if I can actually do that. And see if I can actually share my screen. Of course, I have too many screens up, and I'm hoping that you can see my screen. Can you still see it?
Yes,
Okay. Can you see something that says DIY Exoplanet Transit Studies on your screen?
oh, now we're seeing your slide notes. Before we were just seeing your slide.
Is that right? Okay. Oh no. Okay. I may have to kind of like do this somewhere else. Okay. Well, let me just try it one more time and see. I may have to just work from here if need be, if it's just too difficult. But okay. Well, maybe I'll just go over there and just show it from here. So you're seeing my my screen, I'm hoping. Okay.
We're seeing your PowerPoint and
We're seeing the
the slides on the side, but your slide is nice and big.
Okay, let me just
On my screen.
stop that. And let me just try it one more time and see if we can actually make that happen. Okay, that's always too difficult sometimes. Okay, and I'm trying again, and I'm sharing my screen and see if you can see that presently. Okay, can you see my screen now?
Yes, perfect.
Okay, awesome. Okay. Well, thanks so much. I'm Enrique Gomez from Western Carolina University. I've used this the DIY interface with my college students as well as middle grade students. So DIY exoplanet transits. Why do you want to do this? Why do you want to involve students for this? So the good thing is that there's always a transit going on somewhere, right? And you have a curated list from DIY that have helped us. And here is my appreciation, not just to Mary Dosal, but also to Frank Sienkiewicz and Ibrahim Ibrahim, excuse me, for putting out a great resource for the community, a great tool for teaching. So there's always a transit going on, and we have lots of stars that are relatively nearby. So so that's where the MicroObservatory really comes into play. And it's possible for students to contribute to our research. The cons is that in order to make this happen, you need a lot of data points, just like Mary showed what you need to do in order to actually have a good data set to show an individual transit event. But it also lends itself to have like a large class project where you kind of like outsource the work of doing measuring the brightness, what we call photometry, to small groups of students or even individual students. So now I'll show like a quick next slide. So this is typically what we do with my undergraduate students, and that is that you have observations requests of, say, looking at Qatar 1, and I had like a student named Joseph Minta from Ghana actually work with me. And one of the issues that we have is that the files that the MicroObservatory, most telescopes actually generate, are FITS files, which are really big, right? And they are really difficult to do. And when in the past, when I've used middle grade students working on this, what they had to do is that they had to pull down a big file down into their computers. And then what they had to do is that they either had to process it using a tool called AstroMSJ, or they had to upload it to the cloud to a place where they can actually do it. And that seemed to be a little bit clumsy. But the idea here is to generate something like this, a light curve that tells you what transit event has happened. And this, as an example, is an exotic generated light curve of Qatar 1 that my student actually generated using this public access code, publicly available code. But this is actually what it looks like in the field. So I am showing you students from one of the charter schools in my area called the Catamount School. These are 6th grade students. I had a relationship with that particular teacher for some time back, doing science projects. So I managed to convince her to let me do this with her students. And typically the observation cycle that I've done with this would look as follows. You have like one day where you talk to the students and they actually select one of the stars where with the exoplanets from the DIY calendar tool that Mary just showed you just now. And one way in which the students can actually get ownership of this is that if the students actually vote, right, vote on which star to observe, you actually have a menu, right? And once you vote, then they feel that ownership, then they become more interested to see what they do as a class. And they actually do that whole submission. So you get at least a feeling of what it's like to actually submit observations using a robotic telescope. So they come in and do this. And one of the things that's really neat is that it's possible for you to actually create student accounts under DIY and do it in such a way so it doesn't compromise, for instance, a student's anonymity or privacy, right? So I had the students voted in March of this year, March 2022, 21st of 2022. They voted on this particular transit event, and we were lucky enough that it was clear in Arizona for them to actually do this. And what I did is I generated an account for each individual student, and because I actually kind of like selected it for the class, then I manually parsed out individual observations. So if you have, for instance, 90 observations that you have to do per night, you want to allow the students to do the job of doing the photometry on just a fraction of those images, to do it in such a way so that the class as a whole, they generate the light curve so you have coverage over the entire transit event. So these are all students giving you the thumbs up, whether they feel it was a worthwhile activity or not, except for that guy in the middle for some reason. He was fully performing for the camera. But anyway, so these are actually student observations. Now, let me just tell you exactly how wonderful this is, because in the past, I've really struggled in previous setups to actually have the students download the software, download their images, do photometry with comparison stars in AstroImage J and do it successfully, or even Salsa J, which is more written for more novice or middle grade students. I struggle for them then successfully, but here, because it's all integrated in the cloud, you could do the following. You could have like one class session when you start and actually introduce the concept of photometry to measure the apparent brightness of a star, right? And within a few minutes, they are doing photometry using very much the same tool that Mary just demonstrated. So this is kind of like the light curve that the students actually generated. And we didn't actually manage to make it all the way down to the end. But what's really cool is that this is within half an hour after I showed you how to actually do this job, which I think is remarkable, right? I usually have to do it a few times and spend quite a bit of time with students, particularly in the middle grade, so they get it and are able to actually complete it successfully. So, so you go from like one session where you talk about exoplanets. What are they? Let's vote on what exoplanet to observe. And then the next day you come back and then we have the observations in the pipeline. You have assigned a job of observing individual time stamps of the transit event, and here it goes, right? So this is actually kind of cool. So this is, I did this also with a college level class, and this is, for instance, an April 7th, 2022 observation of WASP 43. And this looks a little bit more like what Mary just demonstrated, where you have a dip and you try to do the fit to see, what is your baseline and how far the dip actually took place. Another thing that I actually did this past year is that I worked with my local university, to essentially do a camp where we do a little bit in depth. And with that, I took advantage of the fact that I have some time on telescopes dedicated for science. So students got to image planets, galaxies they got to do, but I also got to do some activities to do a deeper dive as to what's the meaning of these images. So this particular camp was called Kids Research Exoplanet Watch or Crew. So here they are, just to show that this is the students that on the grade level that are actually able to do exoplanet studies using the DIY interface, right? But before we do that, here's an example of what I have to do. The students don't necessarily know what is the meaning of the image that you are looking at when you're looking at DIY exoplanet search. For instance, they might think that a bright spot might be a star, when in fact it could just be a cosmic ray, or for instance, could be a hot pixel, or sometimes what you have is you have entire rows in your camera of your CCD that are actually bad. So to just get them to think about what is the meaning of this, I created this pool here to show what the pixel instruments are for the CCD. And essentially you use water to represent the light that rains in during exposure time. And then you essentially label them in a grid, and then have the students actually kind of report and do what the processing of your camera actually does, which is kind of like empty one of these things at the time, each pixel, and actually report just how much light was captured. And then kind of just demonstrate, right? You have like a group of students in another room that doesn't know what this thing actually looks like, right? They actually kind of look in there and try to figure out what is the coordinates value of each pixel, how much light was captured, and then they go and write it on a board, right? And then another set of students, what they have to do is that based upon the coordinates on the CCD, and based upon the relative amount of water that there is, they have to reconstruct an image, right? And that's one way of teaching about CCD. And why is this important? Because when you jump into DIY, into the interface, and you zoom in, you see things like this, right? And you can see these vertical lines that tell you that you have kind of like a road that's a little bit iffy, but also so that when you come in and do the photometry and talk about what's called the annulus, right? The circle in which what you're doing is that you are collecting the light and then have to subtract the value of the background light that comes in from the sky, from background sources, so that not all the light that you're getting that circle actually comes from your star or your comparison star. So what do you do? Here's another activity that I did. So this is an idea that I stole from Kate Meredith from the Geneva Lake Astrophysics and SIM. And that is that you do essentially kind of like this circles representing what the circles, the annulus for photometry in the DIY search are supposed to do. So essentially you sprinkle butcher paper with water representing essentially noise, but then you have kind of like clusterings representing the light from the stars. And what you do is that you essentially come in, count what's in the circle, count what's outside the circle or in an annulus to subtract the background. So they hopefully make sense of that activity a little bit later on. It doesn't have to do, but I think that the students actually help to make more sense of this. So by the time in which they are jumping in and doing the DIY search of the planet that they as a group actually voted on to observe and actually do it, hopefully they'll make a little bit more sense of that activity, right? So this is what we did. I believe that this is, I think that this is test 3. That's right. So we did this test 3, and just like Mary demonstrated, so this is going to be the entire group, all the data points that they actually gathered. And here you have like an individual student. So you're seeing the point of view from that particular student, and you as an instructor can actually see how each individual structure did. But what you can see is essentially our errors, right? You see errors. These are things that are probably not part of the did. And I think that's a good thing. I think that the students need to see what it looks like when you make observations that are in fact in error. Maybe then select the right star or the right comparison star, and that is okay. Why? Because you can always cross-check. And what you do is that you can have students observe the same time frame, multiple students observe time frame at the same time, so they can cross-check against each other. And I think that that's an important thing in order to convey science, right? How science actually works, that we have mechanisms for cross-check and to control how things are actually done. Okay. So with that, I think that I'd like to thank again the Center for Astrophysics. You guys are awesome. Thank you for your support that you've given for me and my students. And hopefully you will choose to do this yourselves and have a good time actually teaching science. So we'll just stop there. So thank you so much. Thank you, Mary.
Thanks, Enrique. That was great. I really liked the additional activities to help kids really understand the technology behind the measurements they're making. Those were really, really terrific. Jim Kernohan is another educator who's used DIY Planet Search with high school students. And Jim, I don't know if you wanted to say just a little bit about it and tell us your thoughts about what works and what we could do better.
Hi, everyone. I'm Jim Kernohan. I teach at Milton Academy just south of Boston. I've been using the DIY site for several years. I love it for a lot of reasons. One, it's not canned data. I've been teaching astronomy for 30 years. I have a lot of worksheets, and here students look at this photo, and everyone gets the same answer because it's the answer they're supposed to get. With this site and with real data, there's a lot of uncertainty and there's a lot of noise. And I really appreciate this is how science works. As Enrique said, when you're measuring the brightness of the stars, I have the whole class look at one image, and we're all looking at the same relative brightness of the target star, and we all get different answers. And there's a difference between uncertainty and error that I really try to hammer home. If a student selects the wrong star, that's an error. And that's really obvious to see because their relative brightness will be 20 and everybody else's relative brightness is 0.98. So that error you fix. But then if everyone has 0.95, 0.92, 0.94, who's right? Well, we don't know. And that's the uncertainty, and that's okay. And you have to live with that. So then I take 80 images, I divide the class up. So every student isn't responsible for maybe 3 images of the hour. And if they were exposing it or taking 4 hours of images, they're responsible for like maybe 12 images. So they're getting into the tedium of, I got to place this circle, I've got to place this circle, I got to place this circle. And they realize quickly it would be a heck of a lot better if they knew some computer programming, like a professional astronomer, and had a computer program do all this for them. But like I told them, when you're in math class in a 5th grader, you have to learn to add and subtract and multiply before they give you the calculator. And that's what we're doing here. And when I have the students taking data the first time, they measure the flux from the target star, the fluxes from the comparisons, the fluxes from the background. I have them work out by hand what the relative brightness is. We go through all the math just so that the students know when they hit calculate and record, that's where that relative brightness is coming from. I try to make this as unblack box as possible. I would suggest to any teacher, try it a few times by yourself. The more you do it beforehand, the easier it's going to be. I stress with the students, we're not discovering exoplanets. We're sure these stars have exoplanets, but we're verifying the existence of. Or we're looking at the data, and does the data suggest there might be an exoplanet? And if there is, how big is the exoplanet? What's the tilt of the orbit, etc. So we're not discovering, but we're verifying. And sometimes someone was mentioning the weather. Sometimes the weather is against you and there's high hazy clouds and the data is just not that good. Or the data is the data, but the data you record is just, yeah, we don't see evidence. Okay, well, why not? Oh, maybe there was clouds. Maybe that star was really low on the horizon. So there's a lot of twinkling or something. At the end of the project, you saw Mary's graph of the data. At the end of the project, when most of the time they're convinced we've saw evidence of a planet, I have them look up the first paper for CoRat 3 or TRES 4, and we look at the professionals' data, and it's not any better, especially the papers from like early 2000s. It's really kind of sloppy, but we're doing just what they did. So I'm trying to get it home to them, hammer home that it's not a bright light that goes on, that you have to really try to squeeze out all the information you can from the data. I was just looking at my notes. Okay, Mary, I do have a thought for you. And I don't want to mess up the system, but when with my class, instead of using the target star, could we as a class say, hey, let's use this other star that we think doesn't have a planet around it and all remember what our other target star is, to see what a baseline would be. Because I would love for the students to say, let's look at a star that we're pretty sure probably doesn't have a planet that we can detect, just to see the sloppiness of the data. But I don't want to record any of that data because I don't want to mess up your statistics. Does that make sense?
Yeah, that yes, that does make sense. And Rachel's pointing out this idea in the chat about getting the baseline when the exoplanet isn't transiting, and
Right.
There's some logistical issues for us around that, just because the software behind our graphic system is trying to fold the data across the predicted transit time, and so the stuff that's way out beyond the transit time doesn't fit on our graph. But I mean, there's a couple answers to that, and I think this is a really good topic. I just do want to bring up that we are holding a next summer. We're going to have a summer institute on DIY planet search, and so those of you who would like to, it's a virtual institute. The Smithsonian's hosting it. I would love to have a group of educators who've used DIY and those who haven't, to really dig in and think about some of these things.
One final thing from my point of view, the students have really enjoyed it. It's one of the things that is authentic. It's real. They really dig into it. It's, oh, look, we discovered this thing. It's great. And so their excitement with this is much better than just me lecturing about it or doing a canned lab on it. So.
Right. Well, that is excellent. So yes, seeing more of a baseline so that you can draw a stronger conclusion. Oh yeah, this really is a dip, is definitely a really good thing to do. I do want to mention that this pathway of learning from last week, where we just kind of learned some hands-on activities and modeling what transits are and thinking about that, this week where we're working with real data, this month. Next month, the Exploring Exoplanet series is going to be looking at Exoplanet Watch, and I'm gonna, let's see, which is the black box that, Jim, you say students, and you can use MicroObservatory data with the black box. So your students, once you learn about Exoplanet Watch, are going to be able to follow that pathway from understanding how you make measurements of this changing brightness of a star, to having a tool where they can take those 100 images, put them through the black box, and understand how it comes out with the model at the end, and actually does a professional fit to the student's own data. So that's in January. Exoplanet Watch, Rob Zellum, who is part of the NASA's Universe of Learning team, works with Rachel, who's on the call now. He'll be talking about Exoplanet Watch and how you can use MicroObservatory data and other data as well, if you have a telescope of your own, for Exoplanet Watch. But again, I definitely would love to invite the people on the session here to join our DIY Planet Search community. We have a sign up list so that we aren't spamming you. So we want you to know that you actually want to hear from us. And it's at this bit.ly/signup-DIY. Or if you happen to have your phone with you now, you can, am I sharing? You can hold it up. Am I sharing the screen with the correct thing here, Erica? I just, somehow I'm the green line.
Yes, you are, Mary.
I am. Thank you. Yeah. So anyway, that you can hold your phone up and get the form that helps you sign up for our mailing list for the DIY Planet Search community. And as I mentioned, next summer, we will be hosting 2 different summer institutes around the use of DIY, and it's called Smithsonian Data Labs, and we'll also talk about using another data lab around spectra that actually features some real exoplanet spectra. So we hope that you'll definitely sign up for that. And any last questions before we end? Well, I really want to thank Enrique and Jim for talking about how you use DIY Planet Search with kids, with real learners, because you really help. Both of you have really helped inform us, helped us make some changes to the interface that are helpful, and we want to keep doing that into the future and really help make it as useful to as many educators and learners as possible. So thanks very much. The next session in this series, if you registered for this one, you're already signed up for it. It's the same link, and it will be January. Oh dear, I just forgot what the date was. Hang on, January 18th, 2023 at 4 o'clock. So that will be all about Exoplanet Watch, and we will hopefully see you all then. So thanks very much. Happy holidays, everyone.